So in this video we're looking at the concept of impulse. Impulse is easy to think about in two different ways. First, we just think of it as the change in momentum, which you can work out with your final minus the initial. Or we can think about it as the force applied over a period of time, force times the change in time. So to make something change its momentum, you have to apply that force, and you have to apply it for a period of time. This is Newton's cool thing. So we end up with this formula. The change in momentum, or the impulse, equals the force times by the change in time. Very, very crucial. So our change in momentum is units of kilogram meters per second, and our force is in newtons, and our time is in seconds. So we could use Newton seconds as alternative units for the change in momentum. Now you can't use Newton seconds, I don't think, for momentum, because it's telling you something different about it. The momentum is the quality of quantity. It's a propensity for matter to keep moving. So a large momentum, it means it would like to stay moving longer. Whereas when you're talking about the Newton seconds, the impulse, you're talking about either the amount of momentum you have to add to it to change it to a certain amount, or the force applied over a particular time. So there's a really subtle distinction there, but it's quite important. If you're talking about changing the momentum by applying a force, sometimes it's better to use these units. Okay, I don't want to harp on about that, just think about that a little bit. An example, let me pause for a moment while I think where I was going. Okay, remember, there's a very, very crucial point that we must memorize, that there is no, we talk about conservation momentum, and that'll come in a little bit later, but I want to mention it now. So momentum is always conserved, except if an external force acts. External force acts. Okay, that's a really crucial thing. It almost always comes up in a test somewhere or an exam. So momentum is always conserved except if an external force acts. And say if you have an object that explodes and pushes on itself in different directions, no external forces have acted on that. Okay, they're pushed against each other, but the same object, the closed system, is still acting. Okay. Yep, no, I'll just leave that. Keep that in mind for future. What else do we want to look at? Oh yes, very cool is how this is actually Newton's second law in disguise. So Newton's second law, you may remember if you've watched that video, force equals mass times acceleration. We're going to take that and end up with the change in momentum equals the force times the change in time. So this is just cool. I love this kind of stuff in physics. It shows that these two are equivalent structures. So let's look at our mass, and our acceleration we know is the change in velocity over the change in time. The triangle's not looking that great there. Some of you can see this popping out already. If we take the change in time across to the other side, multiply both sides by the change in time, we end up with mass times the change in velocity. That mass times change in velocity is equal to the change in momentum, and then our left hand side is already the same as what we have there. So if you didn't catch that in the first time through, go rewind and go back through. But that's quite a cool structure, quite crucial. It helps your understanding to see that this is really Newton's second law. I'm not sure if it came up in the Newton's second law video, because it tends to fit better with this change in momentum impulse idea, but there you have it.